Good evening, everyone. Welcome to the Introduction to Electronic class. And it's on March 28th. It's a Monday. It's a rainy day. And thank you for joining. And today we do have a lecture, but next week is spring break. So there's no class next week. And today, maybe just now or after class, I will activate test 1. So test 1 will be available and it's take home. Everyone can spend the spring break to work on it. Or if you have spring break planned, you can also use the following Monday, the next Monday. Not next Monday, it's the Monday after spring break to work on it. So let's see. Let me go to Google and then calendar. Let's see here. We just need a regular calendar. It's too tiny, man. Let's say here. Today is March 21st. So we do have a lecture today. Next week begin with 28 to one more week. So to 4th. No. I'm sorry. From April 4th to April 10th. That's the spring break. And then the next class meeting is April 11th. So we have no lecture on April 11th. And at that time, the class time is allocated, is designated for everyone to complete the test number 1. And if for anyone who has questions, may come here during the test, the time, and then I can give you more hints. Cannot provide an answer, but I can give some hints. And for anyone who complete test 1, that meeting is optional, so no need to. So it's a day we won't move forward. So it's a day to catch up. It's a day to finalize test 1. And then the new lecture, the new lecture after today's lecture will be on 18th, April 18th. And that day we're going to cover chapter 8. So first, let's go to our online book. It's called All About Circuits, pluralcircuits.com. Click on the Education tab and then Volume 1. Today, or so far, we covered these chapters. This is a reading assignment. Last week, we complete chapter 6. That's the divider circuit and the Kirchhoff laws. Today, we are moving to chapter 7. This chapter is called a series parallel combination circuits. One circuit is combined of both type of wiring, series wiring and then parallel method for wiring circuits or wiring resistors. And then the following lecture, the lecture on that, the 18th, let me see, it's on 18th, yes. The next new lecture, that's in April 18th, almost like 3 weeks from now. And we are moving to here, capacitor. And we're gonna cover capacitor chapter. Okay, any questions before we begin today's lecture? So we begin with chapter 7 today, series parallel combination circuits. Any questions? Oh, I'm sorry. I see the microphone symbol is flashing, but I cannot hear anything. I have to adjust my audio settings. Anyone talked to me earlier? I'm sorry, I just realized I cannot hear. Now I can. Gerardo? Oh no, I think I can hear the sound, but cannot recognize the voice. May you adjust the audio? I think it's the microphone. Hello, Gerardo? Sorry, I still cannot hear. Can anyone hear Gerardo's talking clearly? I can't.
Hey Mo, no, I'm sorry. I wasn't trying to ask a question. I think I just unmuted myself on accident.
Okay, now it's very clear. No more accident now. No problem.
Cool. Sure thing. All right.
Anyone have questions before we start? Okay, let's do it. So if we start early, we finish early, we can finish early. And then let's see, today's chapter is not that long. It's not easy, but not that long. It's a kind of short chapter and useful, very useful chapter. Let's see, I also hear some, okay, someone unmuted earlier, that's fine. Okay, I have my chat windows open. Okay, so it's called series parallel combination circuits. And then we only need to focus on two topics on this chapter. If you look at the sessions or the topics in the online book, let me switch to that screen. That can be useful. So here is the online book. Even though here has more names, right, more items listed, but they can be categorized into these two topics, these two categories. Yeah, here. Which means we still cover the entire thing or almost the entire thing on the book. Edward, questions? Okay, let me mute. Okay, so here, 7.1, simplest series parallel circuit. So let's take a look. Let's look at what is the simplest series parallel circuit. What does it look like? Here, this one is the, let me remove the bubble, the circle. Here, this circuit is just the simplest series parallel combinational circuit, or in short, just series parallel circuit. So as you can see, right, so here, if you look at just these two branches, they are connected in parallel. The R1, R2 are in parallel. A leg of R1 connects to a leg of R2. The opposite leg of R1 connects to the opposite leg of R2. So this region, the resistors in this region forms a parallel circuit. So if here combined and merged, right, R1, R2 combined and become a single resistor, this single resistor connected in series is R0. That's the reason it's a series and then here parallel circuit. So I have an animation shows this also. So here the highlighted region R1, R2 are connected in parallel. And that part is not that bad, it's kind of easy, very easy to identify R1, R2 are in parallel. And then which means we can replace these two resistors by a single resistor. And then we can call it such as RP, where P stands for parallel, or any name that makes sense, and that won't cause confusions. Right? So if you use RS, the S can be confused with source resistor. So that's the scenario we should prevent naming resistor in that way. Other than that, other names, they all apply. So here I just call it RP, where P stands for the original parallel circuit. So after merging those two resistors is a single resistor here. This highlighted resistor and R0, they connected side by side, which means they are connected in series. So they can be merged easily. When resistors connected in series, like holding hand, we can simply add them up. So R0 added to RP is the total resistance of the system. And that can be replaced by one symbol, just call it RT. And the T in this case stands for total resistance of the system. So as you can see, we have a original series parallel circuit. After using the tricks and merge them, at the end is a circuit with only one resistor. You may ask, or one may ask, why? What's the point? Why we need to merge resistor and turn multiple resistor to a single one? Because now, right, at this stage, we can apply all the theorems or laws, such as Ohm's law, to figure out current, for example. If we know the voltage source, volt, and then the RT, the total resistance, we can find the current. Once we know the current, we can also find the power. If you also know the time, the total time with power, we can find the energy. Lots of things can be calculated. So this is the reason we should almost always merge resistor. And eventually the system has only one resistor, is for calculation to get other quantities. So let's step back. So earlier I skipped many slides, so don't skip it. I explain from here. So here is R2, and then as you can see earlier slides, we need to merge resistors. Whenever, so far this is true for all the circuits I have seen. I tried many circuits, solved many circuits. This method works for almost all, 100% all circuits I have seen. And then this is the rule of thumbs for solving this type of circuit, solving series parallel type circuit. So first, we need to locate the source. And so far, there's no source, but currently the circuit doesn't connect or hasn't connect to any voltage source. That's fine, but we know the source is going to be connected over here. A voltage source connects to this node and the other node, positive node and the negative node. So the rule of thumb is first locate the source location. It will be here. It will be in this position later on once it's connected. So locate the source location there. And then instantly, right, move the hand or the finger to the furthest point in the circuit from the source. Source is here or will be here. And then the furthest point to the source is R2. So R2 is the starting point. Now we're going to start at R2 at the furthest point to the source to merge resistance. So this is the rule of thumb. So far, this rule of thumb works for all circuits I have seen. Any questions? Okay, cool. So let me copy this and so here, R2 is the furthest point. And we start merging resistors R2, and if you look at the directions, the R2 and the R1, and then afterward, the next one will be R0. So R2 merge with R1, combine the single resistor, and lastly combine with R0. So this is the direction. So again, know where is the source location, instantly move to the furthest point to it. And then next, just start merging all resistors from the starting point towards the source. So later we have examples. So here, right, first we merge R1, R2, that becomes RP, and then start merging again from RP towards left. So the next resistor it combined to is R0. And then now we get RT. Okay, how about let's use examples, numerical examples with numbers to reinforce this learning. And before that, let's also insert a voltage source. We put a voltage source here, and then let's name it VS, where S stands for source. So the source voltage connect to the rest of the circuit. This is a complete series parallel circuit. Okay, the next thing, right, usually once we replace all resistors by only one, the next thing we can do, assume we also know the source voltage. The next step we need to take is to find the current, the electric current in the branch. After that, we can find such as the power, right? This purple means power dissipated almost anywhere. On the R0 resistor, R1, R2, or even the total power dissipation in the system, the total power delivered by the source, like this circle, by the source called Vs. So as you can see, it's pretty important, right? Knowing this or knowing how to merge a series parallel circuit's resistance is very useful. Very useful circuit solving technique. Okay, now here is our example. Looks like my computer stuck a little bit. Let's wait a few more seconds. Wow. Okay, now it works. Okay, so here we still have that simplest series parallel circuit. The reason is simplest because for a series parallel circuit, it must have a branch that's parallel. The simplest parallel circuit is a circuit that has two resistors connected in parallel. But that's the simplest one. And then we need to make series parallels, and we have to connect this to a series circuit. Okay, so the goal, right, the question of this problem is to find the total resistance. And once we find the total resistance, we can find more stuff. So now let's find the total resistance of the circuit. So this is the circuit. R0, the resistors connect to the voltage source later. In the main branch is barely 10 ohm. R1 is 3 ohm. R2 is 6 ohm. Oh, by the way, these are just additional information. 10 ohm, even 100 ohm, I consider is a relative small resistance, small resistor. Even 100 ohm. When we build a circuit, the circuit runs in most small electronic devices. That resistance usually is more than 100 ohm. It can be like 1,000 ohm or even more, even 2,000 ohm. So 10 ohm or even 100 ohm, of course, 3 ohm, 6 ohms, they are very small resistors. The value are small. Perhaps usable, they're usable in certain cases, building some small electronic circuits, such as maybe the earbud. Okay, how about let's find the total resistance of the circuit. Let's review the rule of thumb. And the source will be placed over here between terminals A and B afterward. Not yet, in the future, very soon. Next example. So instantly we need to move the hand or the point to the furthest point to the source, which is R2. And then that's our starting point in terms of merging the resistors. We need to merge it from this point towards the source, AB, terminals AB. Let's do it. So here, that's our starting point. Let's merge these two resistors. Resistor R1 and the resistor R2 are connected in parallel. So we can write in this way. So RP is R1 connected in parallel with R2. These two vertical lines, also called two pipes, represent parallel. Since we have two resistors are connected in parallel, we can use a shortcut formula. I hope that formula is already on your cheat sheet. In case it's not there yet, please put it on cheat sheet. We're going to use this formula a lot. Having this formula or knowing the formula can help solving the problems, the problem in the homework and the tests, or even final exam. So having this formula is very useful, those formulas. The first one is the general formula. No special name, but most people just call it reciprocal formula because every single term in the formula is a reciprocal form. Reciprocal means 1 divided by something. And the first equation, the one in the first top green box, is a generic, is a general formula. It's a formula applied for n resistors connected in parallel. But over here, we have only 2 resistors connected in parallel. We can start using a shortcut formula. That is here, the second one. It's easier, shortcut. Just plug in the numbers and then run a calculation, we get a result. Easy peasy. So over here, I just pick the shortcut formula. For anyone prefer to use the first one, feel free to use that. That also can get a correct answer. Just to me, I think it's a little bit, you just have more steps in terms of calculation. Okay, so here, if you pick the second one, the shortcut formula that is here, the next step is to plug in the numbers, plug in the values. So in this case, R1, the first resistor R1 is 3 ohm. Actually, just one of the parallel branches is one resistor in the parallel branch is 3 ohm. So this is 3 ohm times the other one. The other one is 6 ohm. So 3 times 6 ohms divided by the summation of these 2 resistors, the sum of these two, which is 3 ohm plus 6 ohm. 3 plus 6 ohm. So that is the formula for finding the total resistance in this sub-circuit. Like this portion of the circuit, not the entire thing. We need to do this one first and then move to the next step. So here, what happened? There. Okay, so I suggest we don't worry about a unit. Do not worry about a unit because that does nothing besides confusing us. We know for every number, the unit is ohm, and we are finding the total parallel branches resistance. So if you just work on the numbers, the result is a number in terms of ohm, right? It's not current, it's not ampere, it's not voltage, it's not coulomb. It must be the unit of resistance. That's the reason we just work on the numbers and then later put the correct unit there. So 3 times 6 equal to 18. And then for the denominator is 3 plus 6, that's 9. Again, just focus on the numbers and then append that unit. 18 over 9 is 2 and 2 ohm. So equals to 2 ohm over here. Resistor R1 and R2 connected in parallel. After merging them, the total resistance equals to 2 omega, 2 ohm. That's here. The step 2D. I'm sorry, 1D. Questions? Questions in how we get 2 ohm over here, this equal to 2 ohm. Okay, cool. And the next step, here just like a review. The links here, the chorizo, the sausages connect together. It's like series circuit. Every link connect to another one by one through a string. We're using strings. And then the ladder here is parallel. That's the reason this portion is parallel. This region and R0 together, the 2 parts are connected in series. So now we know R1, R2 are merged, right? Or at least merged virtually. The total resistance is 2 ohm. So we can literally erase these two wires and resistors and replace that by a single resistor. That RP equals to 2 ohm. Now this works in theory, also works in the actual experiment. So this is true, is correct. We replace the original two wires, two parallel branches, parallel wires or resistors to one with only one resistor. When we solve the circuit problems, usually we don't need to draw the circuit step by step. We don't have to. If you know what we are doing, so there's no need to draw a separate circuit or maybe a newer circuit. As long as the answer is right, and that's not mentioned, we have to draw each step circuit in the question. Otherwise, we don't have to. So if you look at these two resistors, the newly combined resistor RP with the original resistor R0, they are in series, like the two links connected using the strings. So here R0, RP, they are connected in series. For series connection, the total resistance is easy. Just the summation, right? Just add all the resistors. So the next step is the total resistance of the circuit is the summation of R0, which is 10 ohm, and then added to RP, that's 2 ohm, since they connected in series. And so 10 ohm plus 2 ohm, the answer equal to 12 ohm. And then next is also a not mandatory step, but if you draw the circuit, doesn't hurt, maybe it's better. So we can combine R0 and RP and then turning this subsystem to one resistor. A system with only one resistor, just by adding this up. 10 plus 2 is 12 ohm. And we can redraw the circuit just by here, 12 ohm. So let me step back, right? This is slide 38. And here is our original circuit. Our original circuit has 3 resistors. This circuit's behavior is same as this circuit. Same value. Even though here has 3 resistors, 10, 3, 6, but after using the techniques we learned, we figure out, right, the total resistance of that parallel series circuit equal to 12 ohm. Any questions? Okay, cool. So why put this resistor? I don't remember. This has nothing to do with here. Yeah, this one has nothing to do with. I should delete these resistors. Okay. Oh, I remember. There is a reason. There is a reason I put that here. But even though this circuit, how about let me duplicate this page. So let me erase here, delete this one, and then put the original circuit here. This is our original circuit. Okay, let me see, 38. Oh, here. There is a reason I drew the resistor here. As you can see here, this circuit is the original, and that one here is the converted. Right? They are same in theory, but there are minor differences comparing to virtual and the reality. So here is the original circuit. And the other side is the converted circuit. In theory, they are same number, same value. However, when we build the circuit using build the actual circuit using the physical resistors and the wires, there are some fundamental differences. So here, we have to find 3 resistors to build the original circuit. The second one, the newly converted circuit, we only need 1 resistor, and that should equal to 12 ohm. As you can see here, need 3 resistors. Here need 1. The one need 3. Perhaps it consume more power, more electric power. Now, the power are not due to the material really for resistance. Is due to the extra component, the compound. Let's say here 12 ohm is the dimension, the size of a resistor. The dimension, the size of it is like this. And here, let's say the original circuit, we need to build the circuit with 3 resistors. Each resistor has the same size, most likely. But the material might be different, but they can also generate lots of heat. When electric current goes through the resistor, go through every resistor, the extra heat can be generated. So in terms of performance, this has better performance. 1 resistor, less heat being generated. Here, 3 resistors, so the heat is almost triple time. Right? Assume each resistor generates certain amount of heat, and now we have 3 of them generating those heat. That's why this is not good. That's the very small differences between 2 circuits, the original one and then the simplified one. Well, actually, there are other reasons, such as here it will be more expensive. Right? Each resistor has a price. Actually, the price are pretty similar. Such as 10 ohm, the value is, let's say, $1. And then for 3 ohm, it's still $1. However, now for building this first circuit, we need to spend $3. $1 for each resistor. We need $3 to build. But here, I just need $1, right? $1 to build it. So this is relatively expensive. That is cheap. Any questions? Okay.
No questions.
Cool. Thank you, Edward. Great. Smart. Fast learner. So let's see here. Original converted. That's the main differences in terms of performance. But in terms of current, in terms of the total resistance, almost the same, or they are same, identical in theory. In the real actual circuit is almost the same. Might vary just a tiny bit, but the general number, they are same. Okay, how about now? Here we have is it a different circuit? Let me see. This one we have 3, 6, 10, and then 3. Oh, okay, same circuit. Now it's the last step of example 1. Okay, how about now? Let's move to example 2. Example 2, right? We need to find the main branch current. Where's main branch current? The main branch current is the current that flows out from the source and entering into the entire system. That is called the main branch current. Let's draw it. So it's this current. So a circuit with the voltage source is showing here. The electric current that flows out from the voltage source, Vs, leaving it and then enter into the system. That current, it is called the main branch current. or there's another name is called the source current, but main branch current makes more sense, more accurate. And so our goal, right, our example 2 is to find that current in terms of a number. It shouldn't be that bad, it's easy. First, let's put the circuit over here. And we know, right, let's move this up. We know these 3 resistors connect in that way can be replaced by 1 resistor. And that's our example 1. We merge 3 resistors and then turn these 3 into 1. Such as here, they are equivalent. So if we need to find the current go to the system, the entire system, we can use the new circuit with Ohm's law. A new circuit has only 1 source and then 1 resistor. So we can apply Ohm's law to find the current IT. And that's easy. Just a reminder, we have 3 Ohm's law formulas. This should be on the first page, the first section in the cheat sheet. This is another formula we use all the time in electronics. Okay, let's see. Since we calculated RT already, so really no need to redo the work, no need to reinvent the wheel. So total resistance is 12 ohm. The next thing, we can use Ohm's law to find the current. Current, if you have the cheat sheet ready, or if you remember this formula, or even that triangle, the Ohm's law triangle, we can all find this equation. The current equals to voltage over the total resistance. The voltage, the entire voltage, send it to RT is 12 volt. 12 volt. And then the total resistance of the circuit is 12 ohm. So here's 12 ohm. Right? Source divided by resistance is current. So it's 12 divided by 12 now. And the 12 over 12, a number divided by itself is 1, and the unit is 1 amps, 1 ampere. So now we find the main branch current just by using the total source voltage divided by the total resistance of the circuit. The number we get is the electric current that flows in this branch. So this is example 2. When we have problems or questions like this type of questions is almost always, this is true for almost always, I mean, always true or almost always true. The first step is to find the total resistance. And then almost no exception. But whenever we have question like this, find the total resistance first. And then the next step is to find a current. We need to know the electric current. That's the next step. Because without knowing the current, we can really do nothing about the circuit. If you look at, let me see, there is a question in the final, similar to here. Okay, next. The next step might be a little bit confusing. I'm not sure. So let's see. I need everyone's feedback later. Not this one. This is related to example 4. Both are important. So example 3, by this time, at this time, we know the current in the main branch. And now we need to find the voltages across R1 and R2, this and that. How much voltage across R1 and how much voltage across R2? That's the next, that's the step here. Okay, let's see. Anyone? First, this is example 3. We need to find the voltage across R1 and then the voltage across R2. Maybe we can find the voltage across both resistors. However, before reaching to that part of the calculation, we need to know one thing. So I call it example 3 and then step part A. find the voltage across this resistor R0 first. And find the voltage across R0. How about let's think about it. Let's spend 1 minute. Let's see if we can find, or if you can get a clue about finding the voltage across R0. So how can we find V? Let's call it V0. From step 2, where we know the current equal to 1 amp. 1 ampere, 1 amp of current flows in this wire, even 1 amp returned to the source. So either here or there, they are either one, for both of them carries 1 ampere of current. So how can we find the voltage drop here? R0. Use Ohm's law. So to find the voltage drops on R0, we can use Ohm's law. Current has been calculated in previous step, and the resistance is known is 10 ohm. So now we can figure out the voltage drops on it. So given the total current, which is the current that goes through pass through R0, and that equal to 1 amp, we calculate it in example 2. Here, 1 amp. And also, let's see what else we know. We know the voltage drops on R0. Over here, how much voltage drops on it? Voltage is I times R, current times resistance. The current is still 1 ampere because, again, they are in series. The current leaving the source is the current entering to the system, entering to R2. So that current times the R0 is the total voltage drops on R0. Is here confusing or is here clear? Any questions? Let me get a virtual hand here. Here, this current is the current that leaving the source, right? From here and then leave it, and then turn and then continue moving, go through it. So this is 1 amps. In order to know how much voltage drops on R0, we need to use Ohm's law. This is Ohm's law. Ohm's law, V equal to I times R. This is 1 amp, R is 10 ohm, so 1 times 10 is 10 volt. And the 10 volt is not super large of voltage. It's 1 volt higher than the 9 volt battery. If you use a multimeter to measure the 9 volt battery, usually it shows like 9.4 volt, close to 10 volt. Okay, so we know this is the voltage we calculated. The voltage drops on R0 is 10 volt. But now let's have a different labeling, same circuit. We need to find the voltage here across R0. Afterward, we can find the voltage at this point. But first, we need to know how much voltage drops on R0. Actually, we calculated equals to 10 volt. The source, 12 volt, right? 12 volt total delivered to the system. 10 volt out of the 12 volt, right? 10 out of the 12 drops on R0. Why is that? Because R0's value is larger than the remaining two combined. So this is the voltage drops here. Source voltage minus that voltage. The leftover is the voltage on this region or on this side in this region. So let's use this picture again. The source provides 12 volt. 10 out of that 12 drops on R0. Only after the voltage goes through this resistor, only 2 volt left. 10 minus the 12 minus the 10 equal to 2 volt. So the 2 volt is between this node and the other node. 2 volt. The parallel circuit together use this 2 volt. Okay, let's see. If anyone have questions, feel free to ask anytime. But now I think we are ready to solve this problem. Example 3, we need to find the voltage across R1 and then the voltage across R2. How much voltage across that or drops on R1? How much voltage drops on R2? How about this? Let's spend this question depends. If you get a concept, this question is you feel this question is very easy. But having get that part, it takes some time to get it, to know, oh, what's the voltage at this point? What is this? And once we got it, it's easy. Otherwise, it can be hard, can be confusing. How about let's spend 3 minutes on this problem. So now it's 6:50. Let's resume at 6:53. So let's work on this individually, independently. It doesn't matter if you can get it right or wrong. It doesn't matter. Now it's just practice. And then at 6:53, let's go over this together. If anyone need a bathroom break, feel free to take it. We resume in 3 minutes, 6:53. If anyone have question, let me know. Okay, it's 6:53. Oh, there's a mistake. Anyone get the answer? Anyone get the answer? What's the voltage drops on R1 and R2? In other words, how much voltage between or across R1? how much voltage drops on R1 or R2. Yeah, as you can see, this can be confusing, right? Since it's just the first time we analyze a circuit like this, it's not that easy. Let's work on this together. At least we spend some time we spend some time think. Perhaps we tried, but we haven't get an answer. That's fine. That's why I'm here. Okay, so now we want to find a voltage across R1 and the voltage across R2. If you look at the labeling, I put C and D over here. C represent the node C, and then D represent the node, the circle, the node D. And then we are looking for the voltage between these two nodes. Right, the voltage between C and D. Let's do an analysis. The voltage between node C and node D is the voltage across R1. And it is the same voltage across R2 because R1, R2 are connected in parallel. This and that, they are connected in parallel, so they must have same voltage. If we know the voltage between C and D, we know the voltage across R1, which is same voltage across R2. So this is our train of thought. So our plan of attack. So we need to know how much voltage across CD. That's fine, not too hard. So from example 2, we have calculated the current in the main branch goes to R0 is 1 amp. And we know the total voltage drops on R0. The total amount of voltage drops on it is the current go through it, pass through it, times its resistance, which is here. Voltage V0 is the voltage across R0 equals to the total current times R0. And then if you plug in numbers, is 1 amps for 1 ampere multiply 10 ohm. The product is 10 volt. And so 10 volt drops on R0. So let's do an analysis again. The source provides 12 volt. Because there's a resistor here and the current goes through it, 10 out of that 12 volt drops on that resistor R0. Let's say there are 12 slices of pizza, 10 slices, right? 10 out of that 12 slices distributed over here to this person. So the leftover should be 10 subtract 10, 12 subtract 10, 2 volt over here. So let's see. So here takes 10 volt, and then the remaining part takes total 12 subtract the 10 equal to 2 volt. In other words, 2 volt is between node C and D. 2 volt is across R1, 2 volt is across R2. One more information, voltage for here, voltage for parallel circuits are same. If you have parallel resistors, right, resistors connected in parallel, all branches have same voltages, same voltage. If C and D, that voltage equal to 2 volt, resistor R1 get 2 volt, resistor R2 in the other branch also get 2 volt. Any questions here? So here, so this is the final answer. But first, we know how much voltage drops on R0 is 10 volt, and then the VCD voltage measured from node C towards D is the total 12 volt by the source, subtract 10 volts drops here, the leftover, the remaining voltage is from C to D. So the answer is 2 volts. Any questions? This is not very easy. However, we do have a few questions. I think one question in test 2, or one question in the final is about series parallel circuit. Okay, if there's no question here, at the end of example 3, we calculated the voltage across R1 and R2. Each one is 2 volt. Maybe a better word here is R1 experiences 2 volt. That's 2 volt from node C to D. R2 also experiences 2 volt from C to D. They don't take 2 volt, they experiences, because both branches are connected between C and D. Each branch experiences same amount of voltage as other branches experienced. So let's look at here. Now, example 4, we need to find the branch currents, which are I1 and I2. These two currents, using yellow arrows to indicate as current, they are called a branch current. The current flows in a branch, not a main branch, sub-branches. So how can we find the current in this branch and that branch? The answer is Ohm's law. Ohm's law is the way to go. That can help us to find the current in every branch. Okay, so let's see. One more time, we know this is 2 volt. Voltage, the volt measured from C towards ground is 2 volt from previous step, 2 volt. And then we know the resistor in each branch. We can find the current. Electric current, I equals to, let's use the formula, equal to voltage over resistance. Current equal to V over R. Current equal to voltage over resistance. So for the current in the first branch, in this branch, is VCD, the voltage from C to D, divided by R1. There. And then plug in numbers. VCD is 2 volt, obtained from example 3, and the R1 that is given 3 ohm. So it's 2 over 3. 2 over 3, 2 volt divided by 3 ohm. Don't worry about the unit. It just causes confusions. Get a number first, and then at the end, we know that must be ampere. So 2 over 3 equals to 0.67. If you use calculator, let's keep decimal form. Fraction form usually not using electronics or electrical engineering, especially for finding current, resistance, voltages. So let's convert this, right? We actually punch the numbers into a calculator and get a decimal form. The unit for current is amps. The step 2, let's call this 2D. 2D is optional. For our class, we don't have to make it look better, which means move the decimal point, get an engineering notation, and then replace the prefix. We don't have to. If we need to, move the decimal point to the right 1, 2, 3 times. So that's 670. And then change here. Reduce the prefix by 1,000. So it's a milliamps. So now we find the current in the first branch, the R1's branch, resistor R1's branch. Before moving to the next step, are there any questions here? Okay. So I assume if it's silence, I assume there's no questions. We can move forward.
I have a question.
Oh yes, Edward.
Professor, on step number 2 in the shaded portion, you went from Ohm's law into that formula. Is that current 1?
Yes.
Step 2?
Yeah.
Okay. So between step 1 and step 2, you went into a Ohm's law.
Yes. VCD was obtained in example 3. So from example 3, here where we get 2 volt.
Gotcha.
Between C and D. And then example 4, we just take that number and then assume this is given or calculated. And then from step 2, this is a Ohm's law formula for finding current. Current is voltage over resistance. So the current in this branch is that voltage, VCD, 2 volt, over that resistance, R1. So that's this formula.
Okay.
Cool.
Thank you.
You're welcome. Thank you for the questions. Thank you for the question. I pretty much, I mean, it's pretty, I'm confident that that's very helpful for other members as well. They may be shy to ask questions or still thinking. Okay, so we can use the similar way with almost the identical method to find the current in the second branch. Second means R2 branch. So let's see, we mainly just duplicate the step. And then we still use Ohm's law formula for finding the current. Current is I equal to voltage divided by resistance. But in this case, I is I2. The current that flows through R2 equals to its voltage, which is the same voltage, voltage across node C and D, 2 volt, divided by that resistance, the resistance in this branch, that is R2. And after that, once we find a number, this is the current flows in that branch. So let's see. Okay, so VCD over R2, VCD 2 volt, we calculated R2 resistance of the second resistor here is given 6 ohm. And next we use 2 volt over 6 ohm. And 2 over 6 is 1/3, but preferably we express the number in decimal form. So 2/3, 2 over 6 is 1/3, and that equal to 0.33 amps. We can do the change here, move the decimal point to the right, 1, 2, 3, which means we multiply this number by 1,000. We need to reduce the prefix by 1,000, so that's milli, 330 milliamps. The electric current that flows in second branch is 0.33 amps or 330 milliampere. Again, writing the answer in this form is not required for this class. It's an introduction to electronic class. We are not required to do everything so advanced, just the important part. As long as we get a correct answer, we're good for now. So here is for the current I2 and the I1 and I2. Oh, we also need to find IT. Actually, we know IT. IT, we know it. I think I just insert this. As you can see, there's no IT in other previous questions. I insert, I add one more question here just to show one law. It's called Kirchhoff current law is true, is valid. So this is example 4 on slide 79. Let's go to preceding slide. Example 2. example 2. Here, in example 2, we know the current, is it this one? Yeah, the current in the main branch, in this branch, equals to 1 ampere. That equal to 1 amps. IT, we calculate it. And now let's go back to here, 79. Let's verify, even though we know it's 1 amps, but let's use this and that just to verify it's right. Let's verify it. Since I1 we calculated, that's 670 milliampere. But I1 is that. Let me see there. And then I2 is the current in this furthest point, that branch, equal to 330 milliamps or 0.33 amps. If we add them up, if we add up these two numbers, we get 1000 milliamps. Let me zoom in. So here, IT, this branch equals to I1 plus I2, because when the current left from the source and entering, enter to the node, it splits. It splits to I1 and I2. So such as I1, I2 are the children of the parent, the main branch, and it's here splits. Part of the total current is I1. The remaining part of the current is I2. And we, from example 4, we know I1 is 670 milliamps. I2 is 330 milliamps. Once we add them up, that is 1000 milliamps, and which is 1 amp. So here, I1 plus I2 together is 1 amp, and that verify and validate IT is 1 amp. Here we got it in example 2. Here we get I1, I2 using different method, but the answers matched. So the input current equal to all the output currents. The law is Kirchhoff's current law, or also called KCL. So here, just one more step to prove this thing. We want to make sure it really works. It's not just work for one case; it works for every case, and it does KCL, KVL for all circuits. Any questions? Okay, cool, great. Now let's see, example 5. As you can see, the question is pretty simple. The circuit is not that bad, but we can expand it to find lots of things. At first, we find the total resistance. That's the step 1, always first step. And then almost always the second step is to find the current. The next step, we need to find the voltage drops on R0, the voltage drops on R1 and R2. Now we are moving to a question for finding the power dissipated on all these resistors. Find the power dissipated on each resistor. So first, about this, let's write down the numbers. These are the numbers we calculated in previous example. Such as the main branch current, this is 1 amps, and then it splits. Here it gets 0.67 amps, this is 0.33 amps. And we may also need a little bit additional information to find the power dissipated on each resistor, on this one, that one, and here. This one is another good question. Now it's 7:13. How about let's spend 3 minutes. Again, 3 minutes. 1 minute for each sub question. Let's find the power dissipated on R0 and R1 and R3. after 3 minutes, let's resume and work on this together. So now it's 7:13 p.m. Let's spend 3 minutes. We resume at 7:16 p.m. Let's work on this independently. Okay, it's 7:17. Let's work on this together. Anyone get answer already? The power dissipated on every resistor. It's a good practice because we will have a few questions in the exams about finding power, and the power is super important topic in electronics. Okay, let's do it together. We have 3 power formulas. The 3 formulas are showing here on the note card. So let me zoom in. I hope these formulas are also on the cheat sheet. I guarantee you use this very often. need this for homework and need this for test 2. Test 2, yes, test 2, and even test 1, and the final exam. First, electric power, P, it is defined. This is definition of electric power. It's defined as the product of voltage and current. And then we actually did this in class. We use Ohm's law formula, the 3 formulas, and the derive, right, combined with the definition of electric power, and then get 2 more forms. Let's say if we only know current and the resistance, we still can find the electric power. So electric power P is the current square, I squared times R. And let's say if we don't know current, however, we know voltage and resistance, we still can find the power in one shot. So that's voltage squared divided by resistance. That's the 3 formulas about. And I add one more slide. That is here. Besides knowing the current, we also calculated those voltages. So let me put that voltage here. Okay, let's see. We can begin with this resistor, right? Finding the electric power dissipated on R0. So at this point, we know everything, right? We know current, we know resistance, we know voltage of that one. So we have freedom to choose to use any formula to find the power dissipated here. So P0, power dissipated on R0, let's say I just arbitrarily pick one formula, the second one, the current square, electric current square times R. So that's IT square times the resistance. IT, the total current, the main branch current is 1 amps. We get it in example 2, 1 ampere. And then R0 is given, is labeled on the picture, labeled on the circuit, on the schematic, 10 ohm. So that formula is changed to 1 amps squared multiply 10 ohm. So is 1 ampere, right? 1 ampere current, but square it, and then after squaring it, multiply the resistance 10 ohm. 1 square is still 1, right? 1 times 10 is just 10. So it's 10. Again, during calculation process or steps, no need to worry about unit that much. As long as there's no prefix, easy. As long as there's no prefix, the answer or the result is easy to obtain. So 1 squared times 10 is 10. And then if you look at just the quantities, power, the SI unit for power is just watt. So just append the proper unit at the end. So here is power dissipated on resistor R0. We can use same method, same formula, or we can try other methods to find the power that dissipated or drops on maybe R1 or R2. R1, let's see. Now, let's say we want to try something new, like for a different formula. We can use V times I. This formula, voltage time current, voltage time electric current, that's the power, electric power. Again, this is not other power, it must be electric power. That's the definition of electric power. Okay, the voltage across R1, that's VCD, and it equals to 2 volt. We got it, we calculated from previous step. Example 3. And then the current that flows through it, we also calculated example 4. That equal to 0.67 ampere or 670 milliamps, either way. And then the voltage time current, VCD, which is here, VCD times the current. Use calculator, we get 1.34 watts. 1.34 watts is the total power dissipated on R1. Of course, we don't have to use that formula. We can use the second one, the third one. They all lead to the same answer. Because over here, we know everything, right? We know the resistance, we know the current, 0.67 amps, we know the voltage, 2 volt. So we can use any formula. No need to, no restriction here. How about now, let's try the next one, finding the power dissipated on R2 this time. The power dissipated here, since we know everything, we know 6 ohm, this is 0.33 amps, or the voltage is still 2 volt, VCD, right? VCD, 2 volt. We know everything, so we can use any formula to find the power drops on it or dissipated over here. So such as, let's call this P2. P2 is the power dissipated on resistor R2. I still use this formula. This formula is, I think most people prefer the formula. It's just product, right? No division, no square, so easy. VCD is 2 volt. And the current that goes through the last resistor R2 is 0.33 amps obtained in example 4. 2 volt times 0.33 amps. So this is 0.33. If you multiply these numbers, equals to 0.66. And then the unit is watt. So let's see. 2 times 0.33 is 0.66. No prefixes here. So unit just the standard unit for power, wattage. So watt. So now we find the power, the powers dissipated on all resistors. And this is the end of example 5. Are there any questions on example 5 or the solution for example 5 before moving to the next example? Okay. Usually, that's all the questions we can ask. That's all the questions we can see when we solve this type of problem. And they are typical questions, very typical. When we are required to solve a circuit like this, a series parallel circuit is a series of questions. They are related to each other, such as the first one, find the total resistance. The next one, find the current. Once we know the current, we can find the voltage drop here and then the voltage on every branch, and then find the power. And then usually the last step is to find the total power dissipated on the system. Yeah, from here, where we know power dissipated on R0, R1, and R2, and they are here. 10 watts, 1.34 watts, or 1.34 watts, 0.66 watts. How about let's collect this number? Yeah, let's write this down, or let's record this number because we need it for the next example. No need to write them down. I already put this on the slide. So that is here. We want to find the power dissipated on the whole system, the entire system. A system of 3 resistors. These 3 resistors series parallel circuit. So how can we do it? Actually, the answer is simple. Here is a note. Power is always additive. No matter resistors are connected in parallel or later in series, it doesn't matter. It doesn't matter. When we need to find the total power consumption, the total power dissipated on the system or subsystem, no need to worry about parallel or series. because that part of the work has been done already. Let's say we want to find a current over here, right? We took that into consideration. We consider, oh, this is in parallel with that, it's in series with here. That's the reason we get a correct current, correct voltage, and then given resistance, we can find the correct power. So the power, at the time we get a power, the numbers are correct already. It's based on here series, based on there or here, they are in parallel. So power are correct. When we add the powers, when we do the power consumption, power analysis, no need to worry about, oh, this is in parallel, we have to do certain ways. That's in series, have to do some other ways, no need to. Just add them up. So in one word, or no, not one word, one sentence, just add all the powers, that's the total power consumption. Power is always independent of the circuit, it's always additive. We just need to add them up. So from example 5, we know P0 here, 10 volt. 10 volt dissipated on this resistor, R0. 1.34 watts, I'm sorry, 10 watts dissipated here. And 1.34 watts dissipated there, R1. And 0.66 watts dissipated on that resistor. To find the total power being dissipated on the system, we just add them up. So total power, let's call this PT. PT is the, oh, I think that's a wrong name. This is P0, P1, and then P2. That's the correct name, 0, 1, 2. And that equals to, let me do a correction here. This is 1. This is 2. P0 is 10 watts. P1 is 1.34 watt. P2, power 2 is 0.66 watts. Just add them up. Use calculator. Together equal to 12 watts. Here. So in conclusion, total of 12 watts of power dissipated on this circuit, on the resistors, on the system. Are there any questions over here on this problem? Okay, cool. Maybe I can add more information here. Maybe a question is why? What's the point of knowing power consumption? There are a few reasons. When power consumption, the first come to my mind, the first reason is, let's say here, right? This one is, this consume 10 watts. So due to this design, the design of this system, this power, this resistor have to consume 10 watts. If we choose a resistor that's 10 ohm, however, it cannot handle 10 watts, this resistor will be barbecued, will be toasted, will be burned out. And then you see first the smoke come out, and then you smell, oh, this bad burning smell. And then perhaps some sparks fly around, spark come out. And then at the end, the circuit is not working. It's burned, it's a big hole in the wire. So we need to pick a resistor that can handle at least minimum 12 watts, preferably a little bit higher than that. In case there's some fluctuation due to current just higher than, or the power consumption is a little bit higher than 12 watt, that still can cover this the spikes. So before moving to the next problem, let's go to that online page. It's called mouser.com. We visited there before. So let me show what I just introduce here using the actual example. So here is our famous electronics online store. It is not online. This is the manufacturer, and then it produce the parts and then sell them here. This ordering them online just the most popular and the easiest way to get them. But you can also visit their company, the manufacturer, the company to buy the parts, or their retail stores. So if we just search resistors, and you remember the resistor we used earlier is 10 ohm. Okay, so here are the list of items, and oh, there is resistors. Oh, smart search. And the search engine is pretty smart. It's filtered and then show all the resistors. Let's say we want to have some resistors. These are the manufacturer, and here are the termination style. Let's use radio. A radio. How about wire lead? No, radio is okay. That's one kind. The other one, let me see. Now this is okay. Just radio type resistor. And let's see 10 ohm, right? In the example, we have 10 ohm. Let's see, do we have it here? Oh, there, yeah, we do. 10 ohm. Click on it. I click on that. And let's see. See, here are the wattage. The resistor has same value, but they may have different power consumption or different capability to handle power. And that term, the name is called power rating. Power rating means maximum power. It's the maximum power it can handle. If power more than that, you'll be burned. So here we have a few varieties of variations. The first one is a 10 ohm resistor with a power rating of 600 milliwatts, not that large. And then we have one can handle 750 milliwatts or even 1 watt. If I switch the screen back to the PowerPoint, let's see what's the maximum wattage. Oh, you need to have this resistor here, right? If you want to put that resistor, 10 ohm resistor over here and make sure it's not burned by this 12 volt source, you need to handle at least minimum 12 volt, minimum. And again, not using 12 volt exactly, need to be higher than that. In case there are some fluctuation in current or power, the gap or the value higher than the power rating still can cover it. So we have to scroll down and find one that's over 12 watts. Oh, here, perfect, 15 watts. 15 watts compared to 12 watts is 3 watts difference. So it's 3 watts higher. In case there are some fluctuations, such as we accidentally turn on or increase the voltage source a little bit higher than 12 volt, that increasing power consumption won't damage the resistor instantly. If you pick 17 watts, that's even safer, or 20, even much better. Much better means more expensive also. 25 volt, okay, that's like double. So most likely we don't use that much. Depends on the application. So here is the reason we need to know, at least we need to calculate by hand. We need to know why we need to, we need to know the power here, power consumption. Power consumption shows or determine which resistor or which component have to be implanted in the circuit. Any questions here? This is in my opinion, that's a very useful information in determining what component we need to get. It's not, even though they are all 10 ohm resistor, but that doesn't mean we can use any 10 ohm resistor. There are some limitations, some restrictions. And so have to balance the cost, balance the power consumption, make sure the number It's not too low. It's not just right between, just right on the boundary. There should be some safe zone or grace period, a grace zone. Okay, so example 6, we determine, right? We figure out the total power dissipated on the entire system. The next question is similar. What's the total power provided by the source? This one is how much power put it on the system, dissipated on the system, delivered to the system. The other one is how much power provided by the source. The question or the answer is not that bad. The answer is same. So in previous example, we get 12 watts. So here, really no need to calculate. We don't have to. We can use 12 volt, multiply the 1 ampere is 12 watts over here, right? The total power voltage provided by the source is 12 volt. Multiply the main branch current, 1 amp is 12 watts. Or we can just say, due to the power energy conservation law, the total power provided by the source need to be same or must be same as the power received by the system. It must be same. No power loss. Assume there's no power loss. This is just circuit analysis on paper, so no power loss. In reality, unfortunately, there's always power loss. So even though here on the paper, it shows, let's say here is 10 watts, right? 10 watts drops or dissipated on R0, but in reality, it's less than 10 watts. Some wattage, some power converted to heat. And the heat is a critical reason, critical problem. It's a reason for power loss. It's a reason for power loss. So that means not, even though in paper, in calculation, we expect to see 10 watts dissipated here, but in reality, it's always less than that. The missing part is the power converted to heat, thermal energy, which is always bad, bad in terms of two reasons. One reason, you're losing power. Power is not free. We have to buy the power from SCE, the Southern California Edison, from DWP, Department of Water and Power, different DWPs. So they are not free. And if you lose power, those power are converted to heat, converted to thermal energy, thermal power. That means we're losing money. And then the second reason is bad to electronics, because heat, right, especially electronics components, are sensitive and fragile to heat. Too much heat accumulated in a region, in a case, in a computer case, in a cell phone case, lots of heat accumulated, increased temperature, and then can damage the components. The components can be burned, such as the semiconductor components. Even the batteries, if it's overheated, it'll be exploded. That's the reason we don't like having too much heat or thermal energy or heat in the or around the electronics components. Okay, let's see. So here we have another question. Now it's 7:42. And here we have another question. No answer here. There's no answer here. Let me see. No. How about this? Let's spend some time to work on this. So the remaining time for today's class, we just work on one more example. And that is example, I forgot the number 9 or 8, but let's call this example 1. And then this example has following circuit with these questions. Here I want to have everyone's opinion. Would you like to work on all the questions at once, and then afterward, maybe 30 minutes or 20 minutes, and afterward we can go over them together? Or let's say we work on one question at a time, spend maybe 3 minutes on this one, and then move to the next one. And after the next one, we move to the question C. Which method everyone prefer? Either, let's say we spend 30 minutes on whole question, and after 30 minutes, we go over all at once. Or we spend, let's say, 5 minutes on question 1, and after 5 minutes, we go over that and then move to the second question. Or anyone just want to work on this offline, and we go over, or I post the answer. Here I want to have everyone's input or opinion, which one just need a few. We spend 30 minutes work on this individually, and then we go over all at once together.
My opinion, sir?
Yes.
I'm going to have to review the lecture once more before I can solve. So if you post it, if you post the answer, that would be best for me.
Okay, cool. I take that into consideration, and then let me have maybe a few more opinion just to see. Thank you, Edward. Anyone also have opinions preferred? If no opinions, I'll follow Edward's suggestion. Everyone agrees, or anyone prefer? How about this? Since I only have one opinion, how about this? Anyone like to work on this, and then after, let's say, after a few minutes we go over that, please stay. And then anyone want to look at the answers, or want to work on this individually and later look at the answers, that also works. Anyone, first I'm going to quickly go over the test 1 questions, and then afterward, anyone want to work on this, please stay. And anyone just want to look at the solutions later, it's okay to exit the meeting and start enjoying the spring break if you have no other classes. Okay, let me go to the Canvas first. This time I convert the questions. Before, all the test questions are in PDF. Everyone have to write the steps, calculation steps, and then take photo or type and submit it to Canvas. But this time I convert them to Canvas like quiz type questions. So let's see, where's my page here? Just let me borrow a few more seconds to find a page here. Where's Canvas? I'm still searching it. Sorry for the waiting. Oh, okay, I found it. So here, there. So I put the test 1 here. So if everyone can, let's say we log in to our Canvas class, and that's the homepage, electronics 2, and here's the session number 11543, and then click on the assignments tab, and then scroll down. Let me publish that. There's one that's published. It's called test 1. Test 1. Just click on that. click on this link, and now it's published. Should be available. Oh, is that right? Let me see. No, that's not the correct one. Here, this is the one. Just update it. Just type one. Maybe I can remove this. This is test one. It's chapters 1 to 5 only, no chapter 6, 7, only chapter 1 through 5. And if you click on here, and then can work on this. It's available from today, March 28, and then due April 11. So we have over 10 days. Over 10 days to work on this take-home test 1. Test 2 is also take-home, and the final exam is also take-home, similar or same format. And then make sure this is due on April 11. We have sufficient time, more than sufficient, maybe more than needed time. This can be done in 2 hours. Before pandemic started, this should be done in class, in the classroom, in person. But now I'm thinking, no, we don't have to. It's an online class. Similar questions, and now we can work on this at home. And if you look at here, together 30 points, and the answer will be, the question will be shuffled. So if, let's say, if I open the test now, and then another class member open the test at the same time or later time, the order of the question will be asked differently, but same questions, same type of questions. No time limit. Let's say if I want to take it now, I open it, and I can leave the system on. It does not close by itself. Let's say if I close accidentally by accident, that's fine. I can log in and then open and resume. So there's no time limit. Just make sure before turning by the due time, the due date, April 11th and the midnight, 11:59 p.m. Anytime before that day, before the time works. And then you can try multiple times. Let's say I did it once, and then later I realized, there's some mistakes I made. That's fine, you can submit again. But this one, there's no real response, which means if you submit, the system does not provide any feedback. You won't know the answer are right or wrong by system. So if you find out there's a mistake by yourself, may try again. The last date to try is the same time, April 11, 11:59 p.m. And can try multiple attempts. And at the end, the system just picked the highest grade. There are some multiple choice questions based on that. And then if anyone, let's say, prefer me to grade trial number 3 out of 5 attempts, just send me a note. Send me a note and let me know which one you want me to grade. So after the deadline, after the submission time, I will start grading. And as soon as I read the note, I know the note, I will grade that particular submission. Otherwise, by default, the system will show me the highest one in terms of the multiple choice questions. I don't want to click on, maybe I can do it. So the first 2 questions are not multiple choice, such as here. Make sure, just type the answer here. And I have to grade this by manually. There's some questions are multiple choice questions. Oh, okay, it doesn't show answers, that's great. Such as here, just click on it, and then that's easy for all of us. And there are some questions such as here require solving circuit. This is easy question, and then just select the correct one. And there are some hard questions. The last 2 problems are time consuming. Question 12 and the question 13, those are relative time consuming. So make sure solve the problem and then put the minimum, put the answer here. Preferably you can show the entire calculation steps. That's much better. Just type something here, such as I equal to 30, V equal to I times R equal to 30 times R equal to 550, for example, and equal to a number. For example, that's great. This is great, and this is for answer for question A. And then question B, continue. That would be great. You can put this in Word document, right? Type the answer in Word document. So this way you have a safe copy in case you have to submit again and again, you don't have to retype everything. And that would be great. And then I look at the answer. If the answers are right, I mark it right right away. If the answer is not right, and I look at the steps and give partial credit. And so if you can put the entire calculation steps, that's superb. So we have this and we have that. If typing, let's say if typing these are just too challenging, too annoying for anyone, you can also write the steps on a piece of paper and take photo. Take a photo and then send it to me. Okay, email to me. Okay, email to me. But preferably you can just put the answer here. Put the answers here. And if other questions are easy, just click on it, click on that, and then you can get a question done. Any questions here? Okay, so this is test 1. Test 2 has similar format, and the final will be similar, same format as this. Before I put this on PDF, everyone need to download the PDF and then write the steps and the answers on piece of paper, and at the end take photos of the answers, upload it to Canvas. Here I think is easier for all of us, especially the multiple choice part. Easy, no need to write answers on paper. For me, the system show me the which answer you get it right or wrong automatically. So easy for all of us. So again, this one, test 1 can try infinite time, no time limit, infinite times until the deadline. This page will be disappeared, won't be available after April 11 midnight, 11:59 midnight. So make sure try this before it. You can try multiple times. At least try once way before that, and then can try again and again. Each trial system does not provide any response, no feedback, so you don't know it is right or wrong. Only can figure out when you realize that's not right. And every time the answer for each question shuffled, but the questions remain the same order. So which means question 1 is always question 1, the first one. Question 2 is always the second one. Just the order of these questions, the options are shuffled. For question 3, this time I open it, this is the first one. Next time, maybe this is the first option. Any questions here? Okay, so again, no class on Monday, April 4th. So the next meeting is optional. That's April 11, because it's the time school require me to require every instructor to give the time for everyone to work on the test. So we have the time, additional time to work on it. And that's April 11. And anyone completed test or have no questions, so that day is optional. But I'm here. I'll be on Zoom from 6 p.m. all the way to the class ends. If anyone have questions or need a hint on solving some problems, please join the meeting. On the Zoom, I'll be in the Zoom and wait for everyone, for anyone who need help, who have questions. And then our next new lecture is on April 18th. April 18th, we're gonna cover an important and it's a little bit challenging, a little bit difficult chapter. Is chapter 12, I think. I forgot the chapter number. It's called capacitor. This one, chapter 11 or chapter 12. It's capacitor chapter. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Chapter 13, capacitor chapter. So if anyone has some time, some spare time, besides taking the spring break or work, and then may take a look at this chapter, just preview, and no need to read word by word, just have a glance, quickly, quickly read it, just to know what kind of topics we're gonna cover. And on the April 18th, we're gonna spend time, one lecture, just cover all these topics. Okay, so I'm going to post that example, the answer for that example, maybe tomorrow. Let me see. Tonight, or tomorrow. And so when you have time, or after you anyone rewatch the video or review, you may take a look. But preferably can work on this. Try to work on this question first, and then compare the result with the solution. Anyone want to work on this now, and later we can work on this together? Please feel free to stay in a meeting. And anyone want to compare, like want a break and then study and then try it, and later at the end compare the result. I wish you have a wonderful spring break. The solution will be posted by tonight. It'll be there tonight. Check on Canvas. Let me see where it will be posted. Let me just borrow one more minute. That's the Canvas page. It's already there, but I will activate it. Let me see. Here. If you're on the home page of our Canvas class, just scroll down to part 2, and then in chapter 7, here, series parallel combination circuits. This one, so far is still unpublished. Here, this will be available tonight. Okay. Any questions?
Professor, real quick,
Yes, Edward.
The last information regarding chapter 7, the series in the parallel, it wasn't public before, but now you're making it public.
Is it?
Is that what you said?
Oh no, it was. I didn't mean to publish now, but it's okay. It's just a exercise problem. On my end, it shows not published yet. A check mark. A green check mark means it's published.
Okay.
But here it's okay. I can publish now. Everyone can take a look also. This is just an exercise problem. It's not a solution for the test. So I can publish this now. I may take a look when anyone is ready, but try the best to work on the question first and then look at the answer. Any questions?
None for me.
Edward.
Yeah, I just wanted to stay after and speak to you.
Sure. Looks like no one have question about Edward. Is that private? Is private? Let's talk at the end, where we can have a breakout room.
Sure. Yeah, I guess private.
Oh, okay, I see. Let me see if anyone have questions first.
Okay.
Anyone? Everyone's here? Charles, Cotley, Gerardo, Jose, Juan, Kyle.
Hey Mo, so you're gonna post the answer for this, and we can just do the work on our own?
Yeah, the answer is
Cool.
there already published.
Oh, where can we find it? I'm sorry.
Oh, okay. It's the Canvas page. So first go to the homepage of Canvas, which is here.
Cool. If it's on Canvas, you labeled it, answer or whatever. I think I could find it.
Yeah, it is right after chapter 7. It's called Series Parallel Combinational Circuit Problem. That one.
Cool. I'm just gonna find it before I leave the class.
Oh, come on, that's a different problem. Let me see. Maybe. No, I'm sorry. I'm going to get the correct one here. This is different problem.
Okay.
Man, let me see that here. Example, but I work on it. I work on it so I can publish tonight.
Good. What is it gonna be under?
It should be here. It should be here. Maybe this one is a. Let me
go back
a note. This is a extra practice 2. I call it 2, and then later once I finish that, I insert here is called extra practice 1.
Cool. Okay. Sweet. All right. Thank you, Mom.
You're welcome. Just below chapter 7, series parallel combination circuit over here.
Okay, great. Okay, thank you. I'm gonna leave the class. I'll see you tomorrow in 1:54.
Okay.
Have a good night.
Gerardo. You too.
Sure thing.
Have a good evening.
Yep.
Okay. Anyone have no questions? And if you like to work on these questions, but please spend the time work on it, and we can compare those. Here, let me see what's the best way to deliver this information. How about let me just share this screen. You can work on this, and then later we can work on this together. Maybe at the time we finish all the questions, I have the answer also. I just posted. So everyone, please, if you're planning to work on it, please start working on question A. Question A is to find the total resistance of the circuit. And the question together may take some time. Maybe now let me create a breakout room while everyone or anyone is working on this. Let me quickly talk to Edward. Before Edward and I go to into the breakout room, any questions? Quick questions?
Yes, quick question.
Sure.
So is class technically dismissed or is it not dismissed?
If you plan to study this later, that's fine. It's okay to leave. It's okay to go, because I think maybe you need to review a few times before working on this. But for anyone who are planning to or want to work on this, and later we can compare the answers, feel free to stay. We have options.
Okay, sounds good. I'll just stay.
Oh, nice. So let's see how to create a breakout room. Let me see. Oh, there. So let me create one breakout room. And then so everyone, I will be back. Please work on the questions. And when I come back, we still wait a little bit, and then we can move to each question. Okay, so Edward and I will go to that room. Again, I'll be back. How to see how to okay.
There we go.
Yes. Oh, I'm back. Anyone have questions or working on it? We can. How come we stop sharing now? I thought even I go to the breakout room, the page still be shared. Okay, let's work on this. Perhaps I can work on this and share the answer at the same time. Let me see. Okay. There are some no breakout rooms. Okay. And about let me work on it, and everyone can watch also. If this is too challenging, can watch. I say at the same time I explain. So first we need to find the total resistance of the circuit. So here that's the circuit. This is the circuit, and then we need to find the total resistance of the circuit. First, where is it? Here. So perhaps right, the circuit is pretty confusing. However, these three branches are connected in parallel. This one, that one, here, right? If it's hard to see it, how about now let's look at that circuit. From there, this one, right? This leg and that leg and these legs are connected together. This leg of R1, this leg of R2, this leg of R3 are connected together. We can redraw the circuit. We redraw and put that to here. This circuit, same as before. Let's close down. So this is the new circuit. Now it's easy, but easier to see. And then how about let's look at that. These three branches are in parallel. By the way, this resistor is the furthest point from here. So these three resistors are in parallel. We can find the total resistance of them. The total resistance is obtained using that formula, the reciprocal formula. 1 divided by the total parallel branch, which is here. Let me erase, okay. 1 over this part. Let me still draw a circuit here. So how about this? And so here is so this equal to RP. Equal to RP. RP, 1 over RP is 1 over R1 plus 1 over R2 plus 1 over R3, right? Using the reciprocal formulas. And then plug in the numbers. 1 over the parallel branch equal to 1 divided by R1, which is 1 kilo ohm, plus 1 divided by 1.2 kilo ohm, plus 1 over the last one, 2 kilo ohm. Okay, so here, if we add them up, that equals to this number, and this number. So using calculator and add these three numbers, three terms, we get that. But remember, this equal to 1 over RP. So to get RP, we take a reciprocal of it. So 1 divided by that is RP. And then use calculator, we use RP equal to 1 divided by that equal to 428.57 ohm. And this 3 parallel resistors combined equal to 428.57 ohm resistance. So the total resistance of the entire system is the 500 ohm. This one 500 added to this part, right? Added to here, which is 428.57 ohm. Together is 928.57 ohm. This is the total resistance of the circuit. Any questions here? Okay, and this is question A, finding the total resistance of the circuit. And next, we need to find the main branch current, which is this yellow arrow. First we know the total resistance. The total resistance is here. This equal to 928.57 ohm. Equal to this. So the total voltage 30 volt over 928.57 ohm, right? Voltage divided by resistance, that equal to current. And the current is this number, 0.0323 amps. And it's not required, but it's good to convert this to scientific, engineering notation. So we can move the decimal point to the right 3 times. So 1, 2, 3, 32.31. So we multiply the number by 1,000. We need to divide a prefix by 1,000. This is milliamps. Any questions here? This is part B, the main branch current. And if no question here, let's move to C. C, we need to know the voltage drops on R0. Well, that's not that bad. It's same as the previous example. Voltage equal to current time resistance. The current is 32.31 milliamps. And the resistance is 500 ohm. The product is the voltage drops on that resistor. So if you punch these numbers into the calculator, it's 16.16 volt. Okay, so that's the voltage drops on here. The voltage drops on R1 or R2 or even R3. Each branch experiences same amount of voltage because they are connected in parallel. So the voltage here is just the 30 volt subtract the voltage drops on R0, which is V0, the difference. So 30 minus 16.16 volt equal to 13.84 volt. The voltage at this point that equals to 13.84 volt. Any questions? So the voltage at here let's see. The voltage at this point is 16.16 volt. So the voltage at here equal to 13.84 volt. Okay. And then next we need to find the current in every branch. The current in this branch, that branch, and here. But that's not too bad because we know the voltage for every branch. Each branch gets 13.84 volt from previous example. So So voltage divided by the resistance equal to current. So if you use 13.84 volt divided by R1, which is 1 kilo ohm, and that's 13.84 milliamps is the current that flows in the branch. And then use the same voltage, 13.84 volt divided by 1.2 kilo ohm. So voltage over resistance is the current is 11.53 milliamps. Similarly, voltage 13.84 volt over 2 kilo ohm is 6.92 milliamps. That's the current flows in the last branch, the R3 branch. Questions? Let me see the chat. Okay, no chat message. So I assume there's no question, but let's move to the next one. Here, we need to find the power dissipated on each resistor. Okay, let's do it. At this time, right, at this point, we know almost everything about each branch, the resistors in a branch. So the power for here R0, we can use V times IT. Voltage drops on R0 times the current. The voltage is 16.16 volt. We calculated in 3 slides earlier. The current is 32.31 milliamps right here. This is the current. I'm sorry, this is the voltage. And then the current is this 32.31 milliamps, go through R0. So the product of these two, 16.15 volt times 32.31 milliamps, this is the power dissipated on R0. The power dissipated on R1, R2, R3 are similar. First, we know the voltage across that one equal to a label. I put all of them here. 13.84. The current is 13.84 milliamps. So if you multiply these numbers, is the power dissipated on R1. And then the voltage multiplied the current in this branch is the power dissipated on that branch R2. The voltage for the last branch is still the same number, right? Same 13.84 volt. The current we get that is 6.92 milliamps. So this times that equal to 95.77 milliwatts. So here we get the power for all 4 resistors. The next question is to find the total power. The total power dissipated on the whole system, on the entire system. We just add this up, right? Add them up. So I capture, right? I keep these 4 powers and then add them up. So adding this up, such as 522.13 milliwatts power 0 plus 191.55 power 2 plus, right, this is power 2, 159.58 milliwatts plus the last power, 95.77 milliwatts. Add them up is 969.303 milliwatts. This is the total power. The power dissipated on the entire system, all the resistors combined, all resistors. Any questions here? Okay, cool. And then we just have one more question, which is the power delivered by the source. This has more than one way, several ways to get it, but I think the most straightforward way is the source voltage times the current flows out from the source, right? The product is the total power delivered by the source. So power equal to source voltage times the main branch current. Source voltage is 30 volt over here, the source. The current is 32.31 milliamps. This voltage times the current flows out from it. And then if you punch numbers into the calculator, we get 969.30 milliwatts. This is the power delivered by the source. This voltage source provides or delivers a total power of 930 milliwatts. And if you compare this power with the power we obtained from previous step, here 969.303, here's 969.30, they are same. There are some small errors due to rounding issues, but they are same. So the conclusion is conservation of energy. The total power being provided to the system equivalent to or equals to the total power dissipated in the system, dissipated on all the resistors combined. All the power, so here, the total power delivered by the source equals to the total power consumed by the system. So this concludes the end of this problem. This concludes this problem. Here are all the steps, but later I'm going to export or save this file and put them on canvas. Any questions?
No questions, sir. Looks good.
Cool. Thank you, Jose. So if there's no questions, I think we can end the lecture here. But I stay here to the end. And I wish everyone have a great spring break. Finally, we have a break here. It's a tough semester.
All right, sir. Enjoy your spring break. Have a good night.
Thank you, Jose. You too. Thank you.
Good night.
Good night, Juan. First, let me pause recording.